Well, I don't know if Newton's third law deserves such an orchestral introduction, but nevertheless, it is important, and we've already discussed the first and second laws. And as review, F is equal to ma, or A is F over m, really summarizes those two laws, because without the first law, you wouldn't even have the second law existing. Namely, the force acting on an object being proportional to the acceleration. That's the essence of mass. Without mass, you don't have inertia, and you don't have any force required to accelerate. So it's a mathematical description of the first law. If F is equal to 0, it means that the acceleration is 0. And if the acceleration is 0, there is no change in the motion. If it's at rest, it's obviously motionless, and it stays that way. If it's moving, it has a non-zero speed, and that's maintained in a straight line as long as some other unbalanced force doesn't act on it. Even Wile E. Coyote accepts the validity of the third law without proof. Now, that wasn't a coyote sound, that was a wolf howl, which sounds actually more cool than a coyote howl. So there you go. And what is the third law? For every action, there is an equal and opposite reaction. And there it is, folks. If you push on it, it pushes back on you. Happens all the time, in every circumstance. You can't avoid it. Speaking of the mathematical definition of Newton's law, let's give that definition, namely that F of 1 on 2 equals minus F2 on 1. So what does this mean? Well, it represents an action-reaction pair of forces between objects 1 and objects 2. So there's two objects, and they're interacting with each other. Now, how do we define action-reaction pairs? Third law, in essence, says if object A pushes or pulls on B, then object B will do the opposite, push back or pull back on object A along the same line of action. Okay? So, as an example, a rifle fires a bullet. A rifle fires a bullet. The rifle is object A, the bullet is object B. And there it is. So we have a force diagram here, beginning at that large dot. The action force. The action force is stated precisely as follows. The rifle pushes a bullet to the right with a 30 Newton force. Okay, so here it is. There's the force of rifle on the bullet. And what about the reaction force? It automatically exists. It's inherent in just nature. You can't have the reaction force be absent. All right, so the bullet pushes the rifle to the left with a 30 Newton force. And that's fully describing the reaction force. So we can graphically depict it as an arrow in the opposite direction, equal size, and let's properly subscript it, F of bullet on rifle. So there's actually 4 things that are contained here in this description, 4 properties, and they are as follows. We got the object exerting the force. You know, in the case of the reaction force, the bullet. The one receiving the force, the rifle. The size of the force, left, and the direction. Whoops, size of the force, 30, I should say, and the direction left. And same things with the action force. So those 4 items are included in every interaction. So you should be able to write those corresponding to any given situation in a problem. So now let's define action-reaction pairs. Bring in the table, and bring in the monkey. That's right, the monkey. Who's not so smart, I mean, look at it. There's this brain case. It's a small brain case. And even as small as it is, a lot of that space is taken up with non-brain material. So it's not too surprising that he doesn't know what an action-reaction pair is. But you are about to understand what it is. We're going to put forces on this diagram now. All the forces are going to be the same size, and they're all distinct. The first one, I'm going to put force of Earth on monkey. That's regular gravity acting on the monkey. Now, where I start the arrow isn't so important here. I'm going to start it wherever I feel like, but it is in this direction, and it's of this size. Okay. We also call that mg. And now we have a force upward. This upward force I'm going to call force of table on monkey. Is not the table pushing up on the monkey? Well, yes, it is. We also call that the normal force. It's normal or perpendicular to the surface of the table. So that's what normal means, perpendicular. But we're not done. We also have another force. And this force is the monkey pressing on the table. Force of monkey on table. And finally, not starting from his eyeball, but acting upward, is another force. I wonder if you can figure out what that is. Any ideas? I'll give you some help. It's force of monkey on earth. Yes, the monkey has a force acting on the earth upward. That's a little strange, isn't it? But it's real. And now, let's look at the action-reaction pairs. Here they are. So we have the force of earth on monkey. The reaction to that is force of monkey on earth. So that's an action-reaction pair. The other one is force of monkey on table. The reaction to that is force of table on monkey. So those are the action-reaction pairs, and there's a very special characteristic that is associated with them. By the way, that's the normal force. And that characteristic is that action-reaction pairs always occur between two bodies. Only two bodies, not a third one. Let's now distinguish that from non-action-reaction pairs, which we will call equal and opposite nevertheless. So first we have force of monkey on the table, and in the opposite direction of the same size we have force of monkey on earth. We also have force of earth on monkey. Equal and opposite to that we have force of table on monkey. But the baby cries because there's something that we have to really be careful about, and that's to note that it's not an action-reaction pair because three bodies are involved. Monkey, earth, table. Earth, monkey, table. All right. So three bodies, not an action-reaction pair. Forces may be equal and opposite, but not action-reaction pairs. So keep that in mind. Please do not overreact to that simple truth.